All right, welcome back from the break. We have one more session before we'll actually take you to MIT.nano so you can see it. But we figured in this session it would be kind of good to tell you a few things. First of all, maybe someone can tell me where the actual clicker is. Just give me 1 second. You have it? Thank you. Amazing collaboration across the Institute. Thank you. So the session on design is what comes next. And I wanted to start it by telling you a few things that we kind of drew into the design of MIT.nano, giving us, call it inspiration of why it is the way the building looks, or even why a logo of MIT.nano looks like this. Now, the actual logo itself is an inspiration from the facade of the building that was provided to us as a vision inspired by Wilson Architects, the architecture firm that worked with us in thinking about how to design this building and make it accessible and welcoming to everyone else. But another hidden clue in this particular design of the logo is notice the periodicity. Everything happens at a particular pitch. You can maybe think of that as the atomic scaling of lamellar planes, or you can think of it as spacing between layers of graphene, or a variety of other ways. But the other thing that it also introduces, despite the fact you have this perfect periodicity, you also have a lot of noise down on nanoscale. And that's where the unevenness of the lines comes from, hopefully evoking the ideas of actually perfection and the difficulties of controlling the nanoscale and designing the world from bottom up. It indeed is not the obvious way to go. You need to think about the details of how to utilize the perfection and the noise in order to get the desired result. Indeed, as we were thinking about how to design MIT.nano as the place to be, to think about innovation, I had the experience prior to becoming full-time a director of MIT.nano, being the Associate Dean for Innovation and thinking about what actually makes innovative processes become. How do you make an invention, and what are the most inventive places on campus so you can launch an innovation journey from them? And it turns out there are 3 ingredients you need to bring together. You need to bring together people of different disciplines, make sure they can truly encounter each other, and make sure they can engage each other. Give them a water cooler, a place they need to hang out around and strike a conversation so biologists can meet an electrical engineer or a chemist and come up with ways of thinking about the world they haven't thought before. So how do we build a place that's easy to reach? Well, obviously, put it right in the middle of the campus. That's the place to go. Oh, and the other thing to make sure to do is to make sure that no one feels like the place is just purely their own. Well, how do you avoid that? Well, one way to avoid that is not to give any professor an office inside MIT.nano. So indeed, there are no offices for any professors, not even the director, inside MIT.nano, and there are no offices for students inside MIT.nano. There are only offices for staff, the truly useful people who run the facility and will make sure your tools truly operate. And at the same time, what this makes is very simply connect the building hence to all the other existing buildings so you can easily reach MIT.nano by about anywhere from 20 seconds to a 3-minute walk from wherever your present office is. You'll still need your personal lab, right, where you can do extremely specialized things. But for anything to do with very complex technologies that many of us want to use, come to MIT.nano, we'll be able to develop it together. Indeed, this was the design that led us to say we better put this building right at the heart of MIT campus, right next to the MIT Dome. Now, that is the soft science, call it, design, meaning socially, I would love to have it this way, but the way to justify it quantitatively is to measure the vibrations in the ground, measure electromagnetic noise, evaluate 5 sites across the campus, and realize this is the mechanically, electrically, and otherwise easiest place to attenuate the noise as needed for the nanoscale experiments, hence giving us the opportunity to indeed build MIT.nano right where we wanted it, without needing to indeed have satellite offices and so forth. Indeed, build a place that's designed for innovation and make it right at the heart of MIT. It's fairly simple to build. Just follow this plan. It has a lot of pipes, and actually it has on the order of tens of miles of pipes and hundreds of miles of wires. And indeed, it has around 214,000 square feet of active space, out of which 100,000 square feet is laboratory spaces. Open spaces, 100,000 square feet. That's equivalent to 100 young professors starting up today, because typically you get about 1,000 square feet when you start at MIT. Well, that being said, what's in those spaces? Well, You'll have, in the heart of the building, clean spaces. Why? Because nanoscale is small, and a dust particle is like a boulder compared to some of your devices. You want to get rid of any kind of dust particles. Well, how do you do that? Well, filter the air over and over again. Does it use a lot of energy? It does. It uses a lot of energy, but we spent about 9 months analyzing different energy efficiency options, considered about 120 of them, to figure out not just how to reduce the energy due to filtering of air, but all the other systems of the building. And using the cleverness that incredibly powerful and knowledgeable facilities department here at MIT has, we were able to combine that knowledge with the work for the architects and the other contractors who gave us a lot of good technical advice. And out of all those hundreds of options, select about 50, 60, 70, I believe, that we truly adapted because they made economic sense and they could make a significant impact. This, to our knowledge, is the greenest cleanroom facility ever developed. And indeed, it will be LEED certified, and we'll tell you that when we finally are ready to make the announcement on the exact certification. I'm told it's going to be extremely high LEED certification as things stand. That being said, besides the clean rooms that are 2 levels, that are 2 stories tall each, right in the middle, down in the basement, the quietest place, the place that has no vibration, or at least can be extremely well isolated, is indeed where our metrology facility is. The very first part of it is we said to design a space that has no vibration, you need a really heavy floor. So how do you do that? Well, you invite 90 cement trucks to come in a matter of a single day and pour all of their cement into a 5 million pound slab that's connected and serves as the inertial slab on which the rest of the imaging facility is built. And if you don't like how quiet that noise is, because you might say it's still only 5 million pounds, a lot of weight. If you can further attenuate it by putting what we think of as a noise-canceling headphones between the instrument and the floor, further providing you, at this point, the level of attenuation of vibration that's simply not usual to encounter anywhere on the northeast part of this country. We are extremely quiet, both electrically, magnetically, and a variety of other ways. We control the temperature to within a degree, humidity to within a % or 2, allowing us hence to not have disturbances as needed for the optical measurements or electrical measurements or electron beam measurements down inside the imaging metrology facility. Similarly, levels of quietness are obtained inside the clean room. And then up on the top floor, we designed a space where you can take all those ideas and turn them into prototypes, spaces that would allow you to actually maybe launch companies. Don't show me just a picture under a microscope as the solution to your technology idea. Show me a prototype. And in order to do that, you need to have the tools of wave photonics that Kristen Van Vliet was talking about to allow us to actually do the integration. Design was from the very beginning at the heart of how we started building MIT.nano. And then we figured out the technical details that led us to be able to build spaces like this. This is what we refer to as the improbability walk. It's right in the middle of the campus, and it runs parallel to the infinite corridor. Actually, it meets the infinite corridor at the staircase, and I often think of that staircase as the staircase of infinite improbability, right? But the improbability walk itself was meant to symbolize the beginning of the other thing we need to do with this building, which is not to just design it for the sake of science and technology, but also to design it for the sake of social understanding of who we are, where we came from, and where we intend to head. The inspiration for the improbability walk was actually given to us by Millie Dresselhaus, a very famous nanoscientist. She unfortunately passed away last year after many, many years of making tremendous differences for the world, both as the first institute professor and indeed first in so many ways, with dozens and dozens of honorary degrees, and indeed tremendous developments of understanding of how carbon nanotubes work, or graphene films, or carbon works as a material itself. Millie indeed found that her journey, based on her background, was such an improbable occurrence. As a result, she felt that if she can do it, others certainly can. Starting as a poor kid in Bronx and then becoming a very notable scientist of her own, she would actually ensure that anytime she had any time to walk from one campus end to the other, she would bring along a student or a young professor or a postdoc just to have a chance to talk to them and give them a chance to exchange ideas. Because she felt when she was a grad student at University of Chicago, and she had those kind of privileges of living in the same neighborhood as Enrico Fermi, a famous scientist in the 1940s, 20s, 30s, she had the chance to walk with him to the university, and in the process she said, this is how I learned what does it mean to be a scientist. She wanted to give that chance to others, and hence we built the improbability walk, allowing us to remember Millie, but also remember that all of our journeys to this incredible place are truly improbable occurrences. There is a plaque on the wall of the Bosworth buildings that commemorates that, and I'll welcome you to see it later today. As you're seeing the rest of the fun activities that will happen in the MIT.nano courtyard and inside the building as well. But there are plenty of elements of design. Again, you can see the frit on the windows that allows this interplay of light and color as it comes through. The yellow light in the back, you can find out why we have some yellow lights in the clean rooms, but the design of the space is just absolutely beautiful, the way that it has actually come through as a comfortable place to live, not just do the work. One thing we, for example, realized is that seeing nature is tremendously comforting for those who are always dressed in white suits and surrounded by white environments. Seeing a little bit of imperfection, a little bit of blemish, someone disheveled walking by is actually very comforting. As a result, we designed MIT.nano to be permeable throughout, and at the same time, satisfy the curiosity of those who are outside, wanting to see what happens to be inside MIT.nano. And there are indeed glorious, glorious spaces inside that indeed should provide a lot of comfort to those who would like to just have social gatherings or indeed peek into the space of MIT.nano. The last thing I'll mention is, as you walk down on the ground level gallery, and there are 2 levels of galleries of Nano on the south side, because we didn't have any offices for professors, we gave all the windows to the rest of us. Meaning all of the southern side of the building on the 1st, 2nd, 3rd, and 4th floor is open to the windows, and we might as well put galleries in there. This particular piece of art was developed by Professor Craig Harter. You're going to hear from him as he steps on the stage to be in a session on the Roundtable. And it is a picture that all of us have seen as an iconic image of MIT. There is one unique thing about it. I call it One MIT because if you look actually a little bit closer at it, and maybe a little bit closer at it still, you will realize that this image is actually made of names that are either written in bold or light print. This is about 300,000 names of anyone who ever attended MIT, taught at MIT, or was a staff at MIT since 1861, its founding, till, roughly speaking, June 2018. If you joined us after June 2018, give us a few years, we'll make a new wafer. Because it turns out this picture is going to be about 6 foot by 6 foot wall on the wall of MIT.nano, but at the same time, we shrunk it down through the power of nanotechnology and wrote it on a single piece of stone, known as a silicon wafer, to the size of about 6 inches. Critical dimension, the line width, is only about 4 microns. Really no big deal. We can go way, way smaller. So we can pack many, many more names if that's really what's desired. The thought was to come up with a way to connect the social aspects of MIT, our intellectual capital, and be able to express it by a single statement, that we are indeed one MIT, and here we are. We are making up the iconic view of what MIT is. This is also a gift of the class of 2018 to MIT campus. That being said, I'm going to stop right here. I'm going to invite our next speakers. I'm going to start with Professor Admir Masic to join us up on stage. Admir is professor in the Civil and Environmental Engineering department. He is a material scientist at heart, and indeed connects his understanding of the civil engineering and material science in very unique ways. Design.
Yes. Thank you for the clicker. Good collaboration. Good afternoon, and thank you for inviting me here. I would like to start with a question for you guys. What is the world's primary building material? What do you think? Anyone? Yeah, close. Concrete. Someone said ceramic. Concrete with its main component, cement. And according to US Geological Survey, by 2050, we'll be producing between 1.3 and 3.4 tons of cement per year per capita. I mean, it's a huge number. And I mean, it wouldn't be such a big deal. But the problem is that for each ton of cement that we produce, we release about 1 ton of CO2 into the atmosphere, making this material one of the major contributors to greenhouse gases. So do you recognize this building here? I mean, it's not a building, it's a bridge. It's a bridge in Genoa that collapsed 2 months ago and killing 43 people. I mean, we don't know exactly the reasons for this collapse and tragedy, but definitely major damage in structural elements and concrete, and also very poor maintenance of this bridge may be the main reasons. But not far from Genoa, in this case, southern France, we find this magnificent structure. And this structure was built 2,000 years ago, and it's part of 50 kilometers of ancient Roman aqueduct. And it's really incredible that after all this time, this structure is still standing. And if you zoom in, you will find people still using it as a bridge. Now, there is another great example of Roman architecture, and this was incredibly studied by our John Oxendorf now in Rome, and this is Pantheon. And Pantheon was built entirely out of concrete. Now, you realize that this concrete survived all of the earthquakes that hit Rome, and also, survived and resisted to all the environmental challenges through 2,000 years, 2 millennia of weathering, whatever, air pollution, you see cars going around. So Roman concrete indeed is an amazing material. But what is amazing about this material, it is not only durable, but also is eco-friendly, requires a lower production energy. And this means that it is much more sustainable. It's also volcanic ash that Romans add sometimes was substituted by bricks, grounded bricks that basically make this material even more sustainable. Now, you do realize that there are extraordinary properties that we would like to implement into our new building materials. So this is exactly what we call antiquity-inspired materials design, and I think that's why I'm in design part of this meeting. And we explore the past for a more sustainable future. And how do we do that? I mean, we need indeed the ancient sample. And this is definitely something this is 2,000 years old Roman mortar that we study using and develop new ways to look into very complex structural hierarchy of these materials. So what we do, we take this and put into a microscope. I must say, after these talks today, my images might look like not great images, but this is a scanning electron microscopy, so not transmission electron microscopy, but scanning electron microscopy of, in this image, each color corresponds to elements. It's not a big deal, but the great about this image is the fact that it's 1.5 centimeters large and half a centimeter high. This means that we can take this piece, put it into a scanning electron microscope, and image all the elements that are contained on that area. And of course, because we are in scanning electron microscope, we are not limited by diffraction, so we can zoom in different parts of the sample, obtaining images that go beyond the diffraction limit of visible light, but also could approach submicron and nanoscale. Now, this is another tool that is very close to my heart because it involves Raman spectroscopy. Raman spectroscopy combined in correlative matter with scanning electron microscopy, and so the elemental composition that you can see here, you can see here is combined with the chemical bonds of element that comes from a vibrational spectroscopy, all in one instrument. So now you do understand where I'm going with all this story. We would like to understand macroscopic properties of these materials, understand it from macroscopic mechanical behavior, for example, and go down to nanoscale and maybe find clues that are behind these properties and translate it into modern concrete materials. Concrete cement materials, cementitious materials. Anyway, so what is beautiful about this work? It is the fact that antiquity has so many of these different materials that can be a source of inspiration. Here, for example, I show Egyptian blue. Egyptians developed this blue pigment that absorbs invisible but emits in infrared, 960 nanometers, very unique property that is being used for many different applications, including fingerprint detection. Mayans, on the other side of the world, developed another blue pigment that is a combination of dye, indigo, and clay. And what is beautiful about this pigment is that it is very resilient. It is resistant to basically boiling strong acids and bases. And the reason to this resiliency is in the interaction between indigo and the nano channels of the specific clay that the Mayans used to make up this pigment. And we are not only interested in designing materials, but also using these tools to understand degradation processes. And I have been working a lot on the collagen degradation in ancient manuscripts. Here I show an example of Dead Sea Scrolls. Now, you see that looking at this slide, summary slide, you do realize the beauty of this moment for me. And MIT will open really new windows to these ancient materials. And I really hope to translate some of that understanding into modern devices and materials. So I'm very lucky also to do this work here at MIT because of our students, not because they are just amazing, but also because I have the opportunity to take students and travel around the world and explore these materials directly in the real-world setting. This is the picture with the current undergrads that we took in Italy, and I will just show you a video that hopefully will work.
So we have 10 undergrads and 5 graduate students. They are very keen to get more knowledge about construction structures and technologies, implementing their knowledge and studies into this playground. I would call it right now playground.
I always wanted to work on projects that are applicable and used all the time in the real world, and cement, concrete, it's the most used man-made material in the world, so I really enjoyed the idea of understanding it at the nanoscale.
We're in a storage room full of treasures found at the Prevernum archaeological site. This stuff is thousands of years old, and usually you go to a museum and it's very hands-off, but here they're like, please touch everything, hold on to everything.
I feel like everyone's getting a really good taste of what is out there in the field, and hopefully we can bring this new perspective of engineering, this new perspective of science back to MIT.
Thank you.
I would next like to invite Dean of Architecture, Hashim Sadikis, to join me on stage together with a roundtable to discuss design across scales.
Vlad promised us a round table. Instead, we ended up with 3 square tables. But I think the layout is actually quite good because we got 3 square tables in a triangular room, including the audience, in an effectively round table discussion.
Close enough. Great design.
Great design. Let me introduce our speakers. From and Craig Carter, who's Professor of Materials Science and Engineering. Pekko Hasoy, who's Associate Dean of the School of Engineering. Carlo Ratti, Professor of the Practice and Head of the Sensible Cities Lab. And Paul Ha, the Director of the LIST Visual Arts Center. We're here to talk about the new frontiers of design and the role that nanotechnologies and the nanoscale plays in helping us expand those frontiers. And truly, design has become a term that is used across very different fields to mean different things. But in general, it's meant to mean synthesis, good values added to the product that is being designed to improve the interface between the product and the human being, and to improve the human experience through different mechanisms. And at MIT, even though there is no such thing as a school of design or a department of design, but we know that there are at least 54 units at MIT that claim design to be their mode of inquiry. There are even hundreds of courses that have the word design in them. And just recently, we started a double major between the School of Architecture, the Department of Architecture, and the Department of Mechanical Engineering, which allows the students to work on art design and mechanical engineering as well. And the frontiers internally are also being pushed. But the word design does allow for that kind of exchange over a round table between different fields and synthesis among them. And my question to each one of you is going to be around how your field helps expand the frontiers of design. But perhaps, Craig, we can start with you and ask you, your work on design tends to say even more that in order for us to really do real design, we need to improve on our expertise in fields that seem to be external to design further than what we think, and that table has to be made bigger. Can you please tell us more?
Happy to. I just want to give a shout out to Vladimir. He was a bit modest when he said that I created that piece. It was Vladimir's idea, and he gave me the privilege of implementing it. So thank you, Vladimir, and that brilliant idea. I've noticed today that a number of the speakers have used design, and always in a different context. And I find it a bit difficult to nail down what design actually means. I imagine that everybody in the audience here, when they think about design, they're thinking about something quite different. And I think the root of that is the fact that design now is a very multidisciplinary topic. I don't know enough about all disciplines to talk about all design. It's too large of a subject. But I know the things that I do certainly include some understanding of materials, certainly, some applied mathematics, some computational geometry, and something that I think is becoming essential in all aspects of design, which is being able to code.
Peko, I know you're working on sports, and that you're working with FC Barcelona, which is the rival team for Real Madrid, my team.
I apologize.
Had I known Vlad, she would not have been welcomed. But you are taking design to the world of sports, and you are also taking it in the direction where there's a challenge, because at the nanoscale, the visual dimension of design, which to people trained in conventional design like myself, is essential. How do you still do what you do and call it design?
Yeah. So just to give a little background, I'm trained as a physicist and a mathematician. So to me, design has always been something that has to do with optimization or functional optimization. And when I started working in sports, I discovered that while that piece is important, there are a lot of other components that you have to bring in. So for example, last week I was having a conversation with the Vice President of Health and Safety of the NFL. And so we were talking about how you introduce new safety gear, how you design new safety gear in the NFL. And she said the first test that the players do when you give them new safety gear is the mirror test. Meaning, does it make me look good? So what I'm rapidly, and this is not just in NFL, this is across the board. When you talk to coaches, and it's not just the aesthetic piece, but there's a level of trust that you have to inspire. Trust that these new concepts that you're coming out with are gonna make me faster, are gonna make me more efficient, are gonna make me more productive. So I've sort of had to change my, my view on how to incorporate all of those aspects as we develop new products. And I've learned that you can't compromise on either side when you're talking about the realm of sports. So, okay, let me go to the second part of your question, was at the nanoscale. The other thing that's come up is that To design these new functionalities, we are now at the point of designing materials and designing functionality at the molecular level. So for example, the product that everybody wants is they want the new Gore-Tex, right? Probably everybody in the audience has some Gore-Tex shoes or a Gore-Tex jacket, and I can tell you right now it's too heavy and it's not breathable enough. So everybody wants the new membrane that is going to replace Gore-Tex. And in order to do that, you have to be able to design at the molecular scale, and you have to design not only something that is breathable and waterproof, but also has drape, which is the aesthetic piece that now has to come in at the molecular level.
Carlo, we think of design within the conventional scale of products to landscapes, perhaps parts of cities. And we think about it as being something that improves on the interface between human beings and their environment. But increasingly, we are seeing it go way out of scale to planetary scale, where we're talking about planetary design. And we're seeing it go into the very human body to improve on things within the body at the nanoscale. Can I ask you, in your work in sensible cities, to reflect a bit on this shift of scale?
Sure. Well, first of all, however, I wanted to start from the definition of design. And I think that's very, very interesting. I think design is something that, Bucky Fuller was actually at one point here at MIT and teaching at MIT, would call a utopia or oblivion moment. And so we keep on thinking about design, like what you say, kind of the mirror test. Is design is beautifying something, I think, there's going to be oblivion. But I think if we look at the very deep roots of design, how we can engage with the big challenges of our time, then that's perhaps what, Bucky Fuller said, utopia. And then, so what is the definition? For me, the best definition was actually given by Herb Simon. I think most of you know Herb Simon, an amazing scholar, a Nobel Prize winner, and so on. And in his book, The Science of Artificial, he says, well, the natural sciences look at how the world is, but design looks at how the world ought to be, or how the world could be. And to me, that's the most beautiful definition because it really sums up all of what we do at MIT. Maybe MIT as a whole is a school of design because we look at how actually the world could be different. And to do that, you might need mathematics, physics, many other things. But then the ultimate thing is looking, exploring how the world of the artificial could be transformed. And to me, that's really why, when MIT was started, was really because of that. Going to the second point, what you ask about, the scales, I think you're right. You're absolutely right. I remember the Bauhaus is a great school of design in the first half of the 20th century, had a motto that says, design goes from the spoon to the city. And for them, was really looking at all the scales. Well, if you need to look at that today, I would say you need to look from probably the microchip or the nano to the universe. And just let me give you an example. At Sensible City Lab, we work a lot with cities. Intelligent cities, we help develop a bit the space of smart cities over the past 10, 15 years. And we look at cities, for instance, if you look at traffic today, you need to look at traffic in the way you might have looked at like 10 years ago or 20 years ago, but also need to look at how something like this in your pocket might allow you to call an Uber, and radically changes the way you do dispatching, the way you actually match people with cars. So it goes all the way from the individual, the nanoscale, the bits being transmitted, from the digital side, all the way to the side and the size of the city, and more, as you say, of the universe.
So we have just changed the name of this institute to MID, the Massachusetts Institute of Design. Paul, on the place of design within this institute, there is a famous diagram that explains the relationship between art and design to be the same as that between science and engineering, in the sense that design brings art to certain applications, the same way that engineering brings science to certain applications. Curating, directing the arts at MIT, how do you feel that relationship with design to be within an Institute of Technology?
So in that note, I want to replace the word design with creativity, and not what is good design, but what creates creativity. And listening to all the brilliant talks this morning, you realize that the new nano building is going to bring amazing technology and innovation and creativity. And what Vladimir has created with this new building is mirroring what MIT has been about all along, which is to create a nurturing environment for creativity. And so we're going to walk over and see the amazing building, and you're going to see a small portion of it dedicated to launch.nano. And for the first exhibition, Vladimir reached out to us and to brainstorm. And he said, what should we show? And I said, well, I don't know. What is about technology? What is about your mission? And he showed me these little tiny pieces of artwork called micromosaics, which I had no idea had existed until he brought to my attention. And he was telling me the history behind it. It goes back to the Byzantine time, and people would take these tiny little grains of concrete or sand or materials and then put them into this mosaic and to bring this incredible design. And so we're going to see 3 beautiful examples of that in the gallery. But in a way, MIT has this amazing public art program, which the LIS is privileged to oversee. And I think all along, MIT has agreed that creativity begets creativity. So as a scientist walks along, a student, faculty members, one never knows when you're going to be hit with an inspiration. And I think by placing these arts and by Vladimir placing the arts.nano gallery in, it really pushes the idea forward to saying it's all about creation, it's all about innovation, and we are creating a nurturing environment where that could happen to you.
Vlad, I don't know how much time we still have.
Actually, it should be
10 minutes, very good. I want to open up the discussion if anyone wants to make comments about anybody else's thoughts.
Sure. Oh, sure. I'll say a couple of things based on what you just said. The first thing is about, yes, I think it's really about how we come together, how humans collide. I mean, I like the idea of being at the center of the MIT campus, creating new ideas. I have a suggestion for Vlad, however. I think you said, the water cooler is the place, that then will bring people together. I think that's a bit sad. I mean, I graduated from Cambridge University. At least there's a tea room there. There's a coffee room. So, but certainly that is really what brings people together. And of course, you don't know what you're going to talk about, and you start from the weather, and you might end up finding the new next great design thing. So, I think that's. But certainly that friction to me is very important. And maybe I think Hashim, you could say about some of the next buildings that MIT is doing the next few years that I think, it seems to me, are really built across this idea of bringing a community together so we can exchange ideas and together be more than the sum of the individual parts.
Carlos talking about the plans to move the School of Architecture and Planning to the Metropolitan Warehouse and to not just think about it as a move, but as an opportunity to bring designers across scales together to work together with the machinery, equipment, but also with the exchange of ideas and the water coolers. Let me switch the discussion to talk about how we teach design, the education of design. And that's a new frontier because we, in the School of Architecture and Planning, somehow owning the pedagogy of design, are receiving a lot of questions from engineering, from science, from other fields, and Sloan saying, can you please teach us how you teach design? We are increasingly interested in the creative, in the heuristic, in the moving from problem solving to asking what if, instead of just solving a problem, saying it could be otherwise, what if? How do you teach it? Engineers are used to problem sets, problem solving. There's one answer. In design, there's not one answer. There are many answers. So how are you changing your pedagogies in order to teach design?
I'll jump in. So we're currently teaching a sports technology class, which is basically a design class. We get the challenges from different industries. And one of the reasons I wanted to mention this is that I think one of the huge opportunities of MIT.nano is unlocking this creativity for students across the institute. Because right now in this design class, I know where to send them to a wood shop. I know where to send them to a laser cutter. I know where to send them to, to get 3D printers, right? So they can prototype things, they can iterate, they can receive feedback. And one of the things that I'm super excited about in MIT.nano is that they're now going to be able to do that at all scales. Right? So there are things that I have not been able to do in the past, in the class in the past, that I think MIT.nano is going to enable.
So my principal job is to teach material science. And so I do give problem sets, but I've began to do something which I think is kind of interesting. And that is, in the middle of a problem set, I will give them something a bit unusual, maybe a little bit surprising. And I'll say, use this as a motif to do something to surprise me. And so it's a very open-ended question, and it kind of gives this environment of creativity and exploration to the students, which I think is probably one of the roots of design.
I think the idea of elegance has permeated engineering. You know, it's not only does it have to be functional, but it has to feel good, look good, has to be elegant. And I know, when I talk to my son, he'll say, that's a really elegant code line, And I was like, just a bunch of codes and it's elegant to you? And he says, yeah. And there is a difference,
Yeah. Maybe if you can add something else, I think all of this is great. I would add a small thing, that today I think we're bombarded with ideas. Design is usually trying to find something, an idea, an artifact. If you take the definition of design before about, how we can look at how things could be, how we can transform the environment around ourselves in a way that does something better. And I think today we have plenty of ideas. And especially with the internet, we're exposed, bombarded to that. And I think one of the things we try to teach people at our lab and in the class is something that was mentioned by Hemingway. In one of the last interviews he mentioned, he said, what's the most important thing? It's the bullshit detector. And what the bullshit detector, because you've got so many ideas, it's important to tell you what is good and what is not good. And that becomes really the thing that can guide you when you get to a really good design.
On that point, I think design has become increasingly important, partly because of the way it's able to simplify or weave lines through the complexities of information and technology and tools that we have. If you think about design in the 1970s, it had a do-it-yourself approach to the technology, transparency. If you think the Babur, the transparent telephones, they made you feel that you could do it yourself. You had access to that technology. But the technology of today is so complex and so inaccessible that the products, like the iPhone, make it much more about, don't worry about it. We'll take care of the technology. All you have to do is use it. It's simplified, but opaque. Maybe that also parallels the increasing interest today in storytelling as being a way of explaining through a very simplified line a series of facts that are increasingly becoming complex. But that complexity is also being challenged by the very technology that enables it. In design, for the longest time, architectural design, we have defined our working table around certain parameters that we put on it and others that we think of as contingencies. We don't want them. Cost is seen as a contingency, cost of construction. Structures are seen as a contingency that we deal with later on. And that there are certain factors like composition, program, form that are essential and the rest is contingent. I think the complexity of the building process is pressing on us to include those factors from the get-go in. And the technology is enabling that. And by that I mean the big data technology, the BIM technology, the AutoCAD technology, the testing technologies, the modeling, prototyping technologies are allowing us to do that. And I feel like the other fields probably are looking at nano as an enabling technology that way. So that design is being taken to its frontiers by expanding the size of the table and saying, okay, now draw a line through it.
Yeah,
now simplify that.
I think that's absolutely true. And I think we've certainly been trying to integrate more and more of that into the classroom as well, so that to help students to understand it's not that first you solve this part of the problem and then you do some design, or first you look at the economics and then you have to integrate all of the pieces from the ground up. Yeah, I think that's actually a really important piece. And I agree with you also that I think it's actually really important in engineering education for students to know that there is not one answer, right? And it's something that I think we have to do better starting freshman year, because freshman year they tend to do P-sets, and there is one answer, and then what that gives us the harder chance, because the harder task, because you have to change the mindset, right? So rather than changing the mindset, we should be teaching them the right thing out of the gates. I think not the right thing. Obviously, you have to get the answer right if you're in engineering, but this linear path towards solutions, I think, is something that's very difficult for students to break out of.
Paul, you evoked the question of elegance, which is a way of bringing the aesthetic dimension of design back in. I feel it's our responsibility to imbue the world with aesthetic value. Every product has to have a certain dimension of it that is pleasing, appealing, complete, enhancing, inspiring of human experience. But when we talk about nano or design at the nano scale, our eyes do not go there. So are we missing out on the aesthetic dimension when we talk about design at the nanoscale or at the planetary scale, or even designing of systems where you're not seeing the whole thing?
I don't think so. There are, it was mentioned quite a few times today that there are many aspects of things like color and sound which have their root at the nanoscale. And then there's emergent behaviors at larger scale that depend on the nanoscale, which gives rise to more interesting color, for instance, structural color. And I think it's a question of knowing how to manipulate, understand, and then manufacture at that scale in order to get an aesthetic object. What that requires is that you can have enough understanding of that scale that you can use that understanding to be creative.
Yeah, and elegance, we connote beauty but also there's functionality to it. And I don't know how many of you know this, but in the museum world, there is a position called exhibition designer. And their job is to purely figure out how we will react to the exhibition and how we go through it, what labels we look at, what information we pull from it. And some exhibitions are designed well, and some exhibitions are designed very poorly. And you can go back into your memories and which museums you visited and that said, that exhibition was fantastic, that I just didn't get.
I've heard a psychiatrist once say that he's a designer of souls. The term is being stretched to new frontiers. Vlad, do we have time to open up the discussion?
No, I think we're going to stop here. There'll be plenty of time back when we get to
Plus, it's not a round table after all. Thank you very much. Thank you.
Thank you.
Thank you.
That's great.
Good afternoon. I'm Bob Millard, the chairman of the MIT Corporation. That's our board of trustees, for those of you who don't know. So it's my job to close out this symposium, which is not as easy as it sounds, because I think anybody who spoke today would be a hard act to follow. But fortunately, I'm not the closer. The real opener is the building itself. I want to really congratulate Vlad and everybody else who built this building. I was there at the beginning when we were first considering whether to build it and how big to make it, and the decision was made to go big, and where to put it, which was not as easy as a decision as it will appear to be from the actual building, because I think a number of people said we had to actually build it inside MIT, which made it about twice as difficult. But I won't belabor that point. So in a moment, I'll invite you all to travel over to the center of campus to really experience this building. But I just want to say a couple of brief words about buildings in general around MIT. It's been, MIT is about education and research, and that has to take place in buildings, but sometimes the buildings really inspire and inform the mission. And throughout MIT's history, there have been real pivotal decisions about buildings that have propelled the Institute forward. This building itself was one of the great decisions. I think it was built in 1961, and if you look in history, great buildings in the history of architecture, you'll find this building among one of the greatest buildings, at least that architects think are great. There have been, which, by the way, still is a terrific building. But there are lots of others. I won't go through them all, just a few kind of notable examples. Building 20, which was here when I was a student here, was built as temporary lab space during World War II, it's where radar was, and some other things were developed. It was meant to stand for just a few years and then be torn down. It was up 80 years later, and actually gave rise to a huge amount of inventiveness and iconoclasm. It was eventually replaced by the Stater Center, which is kind of crazy in its own right, and I assume most of you have been in it. It's quirky and thrilling to be in, and it interconnects a lot of stuff. There's the Koch Center, which took biologists and engineers and put them together uniquely to work on mostly cancer. Right across the street, there's the Brain and Cog building, which I think is the largest such facility in the world, or something like that. And I think we now have a huge amount of brain and cognitive science and neuroscience in it. But I think the most incredible building on campus, in my mind, is the one that was built in 1916, which is the main building itself, the main campus, what we call the Bosworth building. It was sort of remarkable. I'll just say a word or two about that. MIT used to be across the river in Back Bay, Boston, and we outgrew that, and there was a decision made to move MIT across the river to what was kind of lousy land at the time. And the thing that was unique about that building was two things. One, it was at the time, it was the largest concrete building in the world. I was glad to hear there was some discussion about concrete. And the second, even more importantly, was that it was built to house the entire university in one building, which, as best I know, was a pretty unique decision, because every other university, I think, has a separate building for this and a separate building for that, and you sort of, everything's siloed. And at MIT, a conscious decision was made to interconnect all the disciplines. And that culture, that decision, which informed the culture, is still the culture of MIT. So the fact that the Nano building was built in the center of the campus is really a reflection of its importance to the entire university. So, that was 100 years ago. So I think 100 years from now, this building, which is really incredibly beautiful and really useful, will still be informing the culture and research around MIT. So I won't belabor it any further, other than to say thank you very much to everybody who made this possible. Thank you all for being here. And I'm pretty excited and pretty proud. And so on behalf of MIT, I want to invite you all to go across the street to the center of our campus and join me and President Reif and the MIT Corporation, the institute leaders, basically everybody at MIT to host, who will host the faculty, students, staff, alumni for a ribbon cutting ceremony. Congratulations again to everybody. It's been a terrific symposium, and it's great to be with you. Thank you.